Hi, welcome to Engineering Mechanics Dynamics Lecture Notes. I'm Dane Quinn from the University of Akron, and today I'd like to do an example on Cartesian motion. So let's get started. So an automobile accelerates from rest for an initial time, t1, and at that time it reaches some speed. Then it holds that speed constant for a period of time, to time t2, and then decelerates, brakes, and comes to rest as shown in the figure. Right? So the velocity increases to time t1, it stays constant to time t2, and then the car brakes and comes to rest at some final time, tf. So we'd like to find the duration of the braking and the total distance traveled. So if I look at this problem, the known values, the things that we know, are a1, that's the acceleration in that initial period, a2, which represents the magnitude of the acceleration in the braking period. Then I also know t1, the time at which the initial acceleration sort of stops, and then t2, the time at which the braking begins. In addition, I also know that the initial position is given to be 0, right? Because we're dealing with distance traveled here. We know that the initial speed is 0, so x dot at time 0 is equal to 0, because again it says it accelerates from rest. And then finally, we know that the speed, or the velocity at the final time, is equal to 0, because again it comes to rest at that point. However, note that I don't know what the final time is. So that's one of my unknowns. And then my other unknown, right, so let's put those down here, unknowns. Again, this final time. And I don't know the total distance traveled. So that will be x at that final time. So the general idea here is to integrate x double dot to find the velocity and the position. All right, so we want to integrate x double dot, which will give us x dot, and then x. We want to apply my conditions up here. And in particular, we want to apply the final velocity condition to solve for TF. And then finally, we want to find or determine the distance traveled. Right? So that'll be x at TF. So notice that the acceleration here is defined piecewise, right? So it's defined over the interval 0 to t1, and then it's defined over the interval t1 to t2, then finally t2 to t final. So when we go and calculate the velocity and the position, we must also determine those piecewise again. So let's look at this. Let's first start off and integrate to find x double or x dot from x double dot. So again, we're talking about integrating x double dot tau d tau. Tau here is a dummy variable. So when I integrate that from 0 to t, I get x dot at time t minus x dot at time 0. So we can do that. And again, we have to do it piecewise. Right, so if I look at this difference in speed, it's defined over 3 different time periods. Right, so in particular, but in that first initial period, 0 to t1, then we're integrating the constant acceleration. Right? So 0 to t, a1 d tau, which becomes a1 t. Then we have this second interval, right? So that's from t1 to t2. And there, again, we have to integrate x double dot from 0 to t. So we have an initial interval, 0 to t1, a d tau, plus the integral from t1 to whatever my time is, t. But the acceleration during this interval is just 0. So when we work this out, this piece makes no contribution, and this is just a1 t1. So this is the speed, right? The value of a1, which was the acceleration, times the time that we accelerated forward during that initial interval. So that ends up being the speed that we hold constant. Then finally, we look at what happens between t2 and t final. Right, so we're again going to have to integrate this piecewise. So it's integral from 0 to t1, a1 d tau, plus the integral from t1 to t2, 0 d tau, because again, there's no acceleration in that intermediate interval. And then the integral from t2 to t, and the acceleration here was minus a1 d tau. So this ends up being a1 t1 minus a2 t minus t2. So using our final condition, so that was x dot at t final equals 0. Well, t final obviously occurs during this interval, so this has to be a1 t1 minus a2 t final minus t2, which equals 0. So from this, I'm able to solve for t final. T final is equal to t2 plus a1 t1 divided by a2. So again, maybe you want to pause the video at this point and go through and work out these integrations on your own, as well as this relationship. But so then the braking time, the time that we spend braking, which is going to be t final minus t2, is equal to a1 t1 divided by a2. So I can go over here to a time velocity graph and plot these. So we'll start off at rest, 0, and we'll increase linearly in time the speed until we reach a value a1 t1. And then we'll hold that. Right, so at this point in time, we now change our velocity profile, and we hold that constant. Right, so it's going to remain constant for a period of time until t2. So looking down here, this would occur at t1, this would occur at t2, and then we have our final time. And during this final interval, the velocity simply, let's try to draw that better. The velocity decreases linearly in time and comes to rest at this final point. So that's the velocity profile over this motion. So now we would like to turn to the displacement. So we have to integrate again. So again, integrating again provides or allows us to determine x of t. And notice that I'm really only interested in what happens at the final time. So I'm going to integrate from 0 to t final. So x of t final minus x of 0, which again recall that this was equal to 0, is equal to the integral from 0 to t final of x dot. But of course, since x dot was defined piecewise, we also have to go and take this integral piecewise. So this becomes the integral from 0 to t1 of the velocity during that time interval, which was a1 tau d tau. Again, tau here is just a dummy variable. And then the integral over the second period, t1 to t2, of the velocity. And the velocity here was constant. It was just a1 times t1 d tau. Finally, the integral over the last period, t2 to t final. And the velocity of the vehicle at this point was a1 t1 minus a2 tau minus t2 d tau. So again, we have to evaluate this integral. Well, when we do this, we find that x of t final becomes a1 over 2 t1 squared. So that's the first integral. The second integral is a1 t1 times t2 minus t1. And then finally, the integral of this last piece is a1 t1 t final minus t2 minus a2 over 2 t final minus t2 quantity squared. So again, maybe you want to pause the video at this point and work through these intervals to obtain this result, so that at the end this becomes the final displacement. And if I do a little bit of algebra and I simplify, I can write this as a1 over 2 t1 squared plus a1 t1 times t2 minus t1. And then this last piece can simplify to a1 t1 quantity squared divided by 2a2. Making use of the solution for t final, which we found earlier, recall that t final was t2 plus a1 t1 divided by a2. So again, I'll take this, put it up into this expression, and it reduces to this. So looking at, again, now a displacement time plot, we see that the motion is quadratic during this first interval. Right, so, and then constant or linear in time during the second interval, and then quadratic in the final interval before reaching zero velocity. Right? So I can identify these points as T1, T2, and then T final. So again, the motion is quadratic in time. During that initial interval, we have uniform motion, so constant speed. And then we have quadratic in time over the final interval, and coming to rest at t final. So here's an example where we have started with known acceleration that's defined over intervals of the motion, and then worked out the velocity and the position of the object. So thank you very much, and I will see you next time.